Hello. So we're going to continue our discussion. We're going to be covering chapter 2.6 in this video. And we're going to be looking at operations with functions and looking at their domain. So before we get started on this, on operations of functions, we need to look at three different types of functions that we're going to be analyzing in these chapters. First type of function is known as the polynomial function, so it's a poly, and it is any function that can be written in this form. Okay, so any equation, polynomial equation. So a poly, examples of polys are like 3x to the fourth minus 7x plus 10. This would be a polynomial, and it's a function if we have a function that defines it. Another example would be 5x to the sixth plus 10x to the ninth minus x plus 5. So another example of polynomial functions. And the thing with polynomial functions is that their domains, the domain of a poly is all real numbers. So anytime you have a function that looks like this, that's a polynomial function, it's pretty easy to answer the question what its domain is. Its domain is non-restrictive, it's all real numbers. So that's the first basic type of function. The second we're going to be talking about is a rational function. A rational function is a function composed of two polys. So it's a function composed of two polys where P and Q are polys. Okay, example of a rational function would be x plus 5 over x squared minus 7x plus 2. So that is a rational function. Another one would just be like a 5 over x plus 5. They're basically functions that are composed of a poly over a poly, and that's a rational function. And the thing with rational functions is they have a restricted domain. Unlike a poly, where its domain is all real numbers, rational functions' domain is restricted because we can't have the denominators equal 0. So on this example here, this one right here, we can't have x equal to negative 5. Why is this not allowed? Because if we plug negative 5, if we were to plug this into here, then you'd have 5 over negative 5 plus 5, which would be 5 over 0. You can't divide by 0. So with rational functions, typically how we describe it is their domain is all real numbers except for those that make the denominator equal to 0. Okay, so in the example that we just looked at, its domain would be all real numbers except for 5, negative 5, so you'd write it as its domain would be negative infinity up to negative 5, unioned with negative 5 to positive infinity. It's another way of saying all real numbers except for negative 5 in this example here. So that's, you have your rational functions. And the third type of function we're going to be looking at is your radical functions. Now, a radical function is any function that can be written like this, where p of x is again a poly. Okay? And the thing with radical functions is their domain, an example, I'll look at two examples here. Their domain is going to be restricted as well. I'm going to do two similar things to highlight the difference. So, in the first one, here, in our example here, the cube root of x plus 2. Because we're dealing with a cube root instead of a square root, there is no restriction on, you can have negatives inside. So like the cube root of -8 equals -2. So negatives are well defined when you're dealing with odd roots. Okay, so if the number is odd here, then it's okay. Then the domain, so if it's an nth radical and n is odd, then the domain's fairly easy. It's all real numbers. Domain is just all reals. However, in the next example over here, this one we can't have negatives inside because the square root of -4 does not equal -2. Because any number, square root by definition is the value such that when multiplied by itself it equals -4. And there's no number when multiplied by itself equals -4. So this is not defined. So with even roots, if n radical is even, if n is even, then your domain is such that the insides, the p of x, has to be greater than or equal to 0. So in the example above here, our domain would be restricted. It can equal -2, that's the lowest it can go, and it can go up to positive infinity. So -2, you plug it in, -2 plus 2, 0. Square root of 0 is defined at 0. But you can't go any lower than -2. If you do -3, -3 plus 2 is -1. The square root of -1 is not allowed. You can go larger than -2, like 5. 5 plus 2 is 7. Square root of 7 is defined. It's an irrational number, but it's not imaginary, which makes it it's a real number. So, again, with radical functions, you have to first look at, is your radical even or odd? If it's even, then your domain is such that the insides have to be greater than or equal to 0. If the radical is odd, then your domain is all real numbers. Okay? So those are your three different types of functions that we look at in this chapter. But none of this has to do with operations on functions. We just had to define the three main types of functions we're looking at. And what we're going to be doing in this chapter, what it's about, is really operations on functions. And what we're going to be doing is we're going to be looking at 5 operations. I'll first do the 4 basic operations in one go, and then the last one, which is composite, when you're compositing a function inside, that's a little bit harder, and we'll cover that just by itself. So let's go through the basic operations. So basic operations are adding 2 functions, subtracting 2 functions, multiplying 2 functions, and dividing 2 functions. Okay? So the easiest way to do this is just show with an example. So I'm going to choose choose 2 functions here. We'll call f of x equals x minus 5 and g of x equals x squared minus 1. And we're going to be performing these 4 operations on these 2 functions. So what's added? So f plus g of x is you just add the two functions. So you have f, which is x minus 5, and you're adding to it g, which is x squared minus 5, minus 1. Add those together, you get x squared plus x minus 6. Okay, so that is the f plus g function. We've added those two functions together. Okay. Next, let's look at subtracting two functions. It's going to be just as easy. You just are taking the f function and you're subtracting in parentheses the g function. You're going to change your sign on the g functions, then combine them to get that, and that's f minus g of x. Okay, what about multiplying two functions? So if we're going to multiply two functions, f of g of x, you're just multiplying them. So you take f, which is x minus 5, multiply it by x squared plus minus 1. That's what it originally was. And you just multiply it out. So x times x squared is x cubed. X times negative 1 is negative x. Negative 5 times x squared is negative 5x squared. Negative 5 times 1 is positive 5. And I might as well write it in descending order. X cubed minus 5x squared minus x plus 5. And this is your f of times g of x equals that. So we just multiplied them. Okay. Lastly is division. And division is just done the same way. Just have your f, which is x minus 5, divided by your g, which is x squared minus 1. Now, and we're done with division. The only thing on these that they're going to be asking is, what's the domain? Well, let's look. I'm going to look back through these and let's analyze, figure out what the domain of these functions are. First off, what's the domain of f and g? Well, the domain, I'll be writing right here, domain of f, because it's a poly, and if you remember polys, the domain's all real numbers. Well, what's the domain of g? Well, g, because it's also a poly, the domain is all real numbers, all right? So then if we look at f plus g, since if you're adding two polys together, you're going to get a poly. And the domain of polys are all real. So this, when you're adding two polys, you're going to end up with all real numbers. What about subtracting two polys? Again, it's all real numbers because you end up with the poly itself way down here. And its domain is still a poly, so its domain is all reals. Same with multiplication. End up here, which is still a poly. It's a larger poly as far as number of terms, but its domain has not changed because it's still a poly. Now it comes to division. Well, with division, it's a little bit different because remember, if you're dividing two polys, that's the definition of a rational function. And rationals, if you remember, the domains are restricted such that you can't ever have the denominator equal 0. So division is kind of the oddball here where you have to actually think about what the domain is. And since we can't divide by 0, x cannot be either a positive 1 or a negative 1, because you plug either of those in, you're going to get 1 minus 1, which is 0. You're going to be dividing by 0. So the domain on this guy is all real numbers except for those that make this bottom equal to 0, and those numbers are x equals plus or minus 1. So your domain on this guy is going to be negative infinity to negative 1, negative 1 to positive 1, and then positive 1 to infinity, which is another way of writing all real numbers except for negative 1 and positive 1. So division is the one where you have, when you're just dealing with polys, where you have to figure out, look at it more conclusively. Now, let's go to another example here. Instead of adding two polys, let's add maybe two radical functions together. It'd be a little more complex. So let's look at example number 2. Let's have f of x equal to x minus 3, and g of x equal to x plus 1 square root. So these are both square roots, so they're both even roots. And we know that even roots are such that they can't be negative on the inside. So we know f, the domain of f is everything's got to be, it's 3 and greater, right? That's the domain of f. Okay, if you're less than 3, you're going to get negative on the inside of f, of the radical, of the square root. With g, if you have to be greater than or equal to negative 1. Okay, because negative 1's allowed, because negative 1 plus 1 is 0, square root of 0 is still 0, but anything less than negative 1 isn't. So then what is f plus g of x? Well, it's just the two functions slapped together with a addition between them. But now it does change the domain. The domain is the intersection of the two domains of f and g. So your new domain is going to be the intersection of these. If you intersect those, here is the first one. Here's 3 going this way. Second one is down here. It's going to be negative 1 going this way. Well, what's the intersection? Well, the intersection is where the two overlap. Where do they overlap? I'll do it in blue here. They overlap here at 3. They're both going this direction after 3, right? So this is the overlap, which is just this guy here. So the domain on the new function will be the more restricted domain, is what it's basically getting at. Okay. Okay. Now let's look at practical examples with this. So how does this work out, again, with operations? Well, in a practical example in the book, they talk about, they create these functions. They have a function of birth. So let's say you have a function that represents birth rates in a country after the year 2000. So, and it's looks like this. Okay, and this is your birth rate in X years after 2000. And then you have a death rate, which is maybe this function. Okay, so then you have birth and death, and then say they want you to use these two functions to create a new function, which is the population growth. If you know anything about population growth, it's birth minus deaths. So you have a population growth if your births are greater than your deaths. So we're going to be doing b of x minus d of x. So there's an example of taking these two functions, doing a function operation, here's subtraction, and getting a new function. We'll call this growth, your growth, population growth, p growth, pg. And you do it by just plugging them in together. So, and doing your subtraction. And don't forget your parentheses anytime you do subtraction with this function notation. That, now you would distribute the negative, right? And then combine like terms, and that'll give you your p of g. And then you're going to take p, this population growth function, and you can answer questions like, what's your population growth based upon X years from 2000? Okay, so that's examples of how these operations, I'm not going to work through it any further, but it's how operating on functions would be used in real life practical problems. All right, so we talked about the 4 basic operations with functions. I mentioned that there's a 5th one. The 5th one's a little bit more involved, so I'll just cover it by itself and cover it last. And the 5th operation is called composition of functions. And all composition of function is it looks kind of like this. So you're going to have f of g of x. And what f of g of x is it's you take the f function, you plug the g function in for x in the f function. So f of g of x is the f function with g plugged in. G of f of x is the g function with f plugged in. And these are not, this composition are not, don't think that they are commutative. Multiplication is commutative. This is not multiplication. So f of g of x is not necessarily the same thing as g of f of x. So don't just assume that. So an example of what this composition of functions are, it's the best is just to look at an example to figure it out. So let's say we have an f function. F function is 3x minus 4. We have a g function. G function equals negative x squared minus 2x plus 6. Okay, and let's say we want f of g of x. Okay, so we're wanting this. Here, I'll just rewrite it. F of g of x. So what you're doing here is it's saying you're plugging your g into f. So we're going to take the g here, and we're going to plug it in parentheses into x. So f of g is the g function plugged into f. So where you see an x in the f function, you're going to replace it with the entire g function. There it is. There's f of g of x. Okay, and we can go ahead and FOIL it out. Combine like terms. And you get that. Now, just to show you that g of f is not the same thing, let's do g of f. G of f of x, that is f plugged into g. So now we're going the other way. We're plugging, we'll do this in red. So this one in red. So we're plugging this guy in for the x's. So go ahead. So here's in your g function, which is negative x squared, you're going to replace the x squared with 3x minus 4 in parentheses. The x squared becomes negative 3x in parentheses 3x minus 4 squared, because that's your x, minus 2. And what's your x again? Your x is 3x minus 4. And then we have plus 6. Now if you're to FOIL this out, here you get negative, this would be 9x squared minus 24x plus 16 minus 6x plus 8 plus 6. Now distribute the negative here and combine like terms. Eight plus 6 is 14. So now combine like terms, you get negative 9x squared. 24x minus 6x is 18x. And then negative 16 plus 14 is negative 2. Notice, these are not the same. So f of g is not the same thing as g of f. That's the whole point of doing that. They can be, but for the most part, they're not. If it is, it's because of some weird circumstances. So that's composition of functions. We're composing two polynomial functions. Let's look at composing maybe two rational functions. So let's say we want to compose, here's f of, I want to get back to black. Let's say we have these functions here, and we want to compose them. Well, these are rational functions, and when you compose them, so we're doing f of g of x. You're plugging g in for x in f function. So when we plug that in, your x is going to become 3 over x, like that. So notice this guy replaces your x in the f function. Then we have to work it out. You have to rationalize this, the denominator. So this has to be x over x. So you're going to have 3x minus x over x. Now that they have a common denominator, you can combine them. 3 minus x over x. Then you're going to change, flip. Keep the top the same, flip over the bottom, and you're going to end up with, this is going to be 2x, 3 minus x. So that's your f of g. Okay. Then they're going to be wondering about the domain. How do we figure out the domain on these? Well, remember with rational functions, they can't be, the denominators can't equal 0. So if we look at your composite function here, we can't have 3. So x equals 3 is not allowed because you'd have 0 there. But because it's a composite function, we have to also look at restrictions on your g. Since you're plugging the g into the f, g has its own restrictions, and g, 3 over x here, x cannot equal 0. So you're going to use the restriction on the g domain and the restriction on the overall f of g function to get your domain. So your domain is all reals, so all reals except 0 and 3. And then you're like, well, what about, f of x, the original function, had a restriction of you couldn't equal 1. Well, the original function, f of x, was changed by g. So we only look at, when you're looking at domain of these composite functions, you're going to look at how g is restricted and how the overall function is restricted. Okay? So the overall functions was restricted at here. That's the overall. The g function, it was restricted here. So then we use this blue and green. We don't worry about, you can't have, we know that x cannot equal 1 in the original, but f, we don't actually use f except to plug g in. So we don't worry about this guy here. Okay, I hope that explains with domain, looking at composition of functions. The last thing in this chapter is decomposition, which is going backwards. And what they're going to do is, this is just a little bit of intuition. They're going to maybe give you a function like this. And they're going to say, can you rewrite h as a composite of two separate, more simple functions? And the answer is yes. You could say f equals cube root of x, and g equals x squared plus 1, and then h we could define as equaling f of g of x, which is the g function here plugged in for x, and it'll return this guy here. Okay, so that's decomposing. They're going to give you a function and see if you can break it up into two compositions. There isn't really a procedure for doing that. You just intuitively, you look at it and figure it out. All right, that's it on this chapter.